I'm going to go ahead and get started, and please ask questions as we go along. But I'm going to go pretty fast, but I'm going to repeat stuff because I really wish I had a huge whiteboard to explain this with, because the topic, it just kind of it's all intertwined, but there's a lot of it. So you'll see why by the time we get there. I'm going to be flipping back and forth a lot. Okay, so let's get going. So tonight, a little bit of logistics as usual. Then we're going to basically develop neural networks from scratch. In a way, the best way that I have seen. I've seen many different ways: neural network, back propagation, forward propagation. I've seen it develop. I've seen it presented many times, and I picked the best one, and that's kind of what I've been sticking with in all my explanations. So it's completely accessible. Everybody that knows just a little bit of math can do it. And we're going to copy it we're going to mimic it with a program. So you guys are going to get it. You're going to become experts on it tonight. Knock on wood. And if not, then just go back and look at all the equations again. And I'm going to give you a good website to look at. That is where I got this from. That explains it. And hopefully you'll get it from this. And this is like the quintessential. This is what makes machine learning. Okay, this back propagation. It's the way machines learn. It's the iterative. It's the way we learn. It's iterative. You take you pass back through your error. It's negative reinforcement or positive reinforcement. It's not just look at something, memorize it. It's do something. Is it right? How far off is it? Improve a little bit. So that's what we're going to do tonight. We're going to all improve a little bit with this knowledge. So, okay. So, so what we're going to do this with is, okay, we're not going to use the model libraries to develop this. We're not going to say, Python, give me a neural network out of scikit-learn. Keras, give me a neural network, and then add a layer to it. No, we're not going to do that. We're going to actually see all of the code behind it. Okay, and we're going to do this with a very basic, very popular data set, the XOR data set. It's very small, very good for this beginning application. And then we're going to talk about feeding forward through the network, and then we're going to do a detailed explanation of the back propagation, going backwards, and then all the Python code to go with that. Then we're going to take the exact same code we just developed for this XOR data set, very small data set, and apply it to a bigger data set, the Iris data set, which we went through last week. And then we're going to talk about the homework, which will be very similar to last week in that I want you to improve on what we do tonight. So be thinking about that as we go through. Some basic stuff, me, and my LinkedIn. Here's my GitHub for this. It's lectures within Deeper Side of Learning. So definitely go there for for this code that we're going through. Very, very important. And you will be able to follow along if you go out there to Deeper Side of Learning, the lectures. You'll be able to follow along somewhat. Okay, I'm going to do this a little bit different than the way the code is out there. You'll see, but still, the code is it. We end up with the same code in the end. Okay, and what we're going to do tonight. Okay, we are not going to do all of this. We're going to do a couple of things in this. When I started putting this part together, I realized that we don't need a lot of this for what we're going to go through tonight. I went ahead and listed it all. This is pretty much all of the linear algebra and statistics that we're going to need for this class for typical machine learning, typical data science. But we are only going to go through what we're going to need tonight, and it's just a couple of slides, so don't worry. Okay, so right into it. Some definitions in machine learning. Okay, let me check, make sure no questions. Any questions so far about what we're going to talk about tonight? Let me pull up chat real quick. I want to make sure that I'm not missing anything. Okay, good. Nothing at this point. So please stop me anytime. Q&A might pop up a little bit bigger in stopping me, but yeah, under the chat you can ask questions there. All right, so some definitions in linear algebra, some very basic stuff. A scalar. What is a scalar? It's one number, any number. Could be 5, could be 5.5, any value, any number. A vector, however, is a bunch of numbers, and some people define vectors, only as n by 1, not necessarily 1 by n. And what it means is rows and columns. N rows, 1 column. So I showed an example there, 5, 4, 3, 2, 1. That's a vector that's 1 row, so 1 by n elements, 5 elements going across. And the 5 numbers are that. Okay, so now let's take it one step further. A matrix is n by n values. It could be also n by m if it's square matrix. But here's an example. This is 2 by 3 matrix, 2 rows, 3 columns. So then you can take it n levels beyond that to what's called a tensor, which is more than just 2 dimensions. N by m would be 2 dimensions. A matrix is 2 dimensions. Vector 1 dimension, scalar 0 dimensions. Tensor would be a matrix of matrices, or a matrix of vectors, not a matrix of scalars. That would be just a matrix. So there's an example of a tensor there. It's a bunch of 1 by 3 matrices, 1 by 3 vectors, you can call them that, in a vector of 2 by 3. So there you have it. There's some definitions that you got to get used to. And then matrix multiplication. Okay, very simple concept. Most people get this. I have seen this before. At one point, probably everybody in the class has seen it before. Okay, we got a question. So 1 second. All vectors in tensors should be of the same size. Yes. I've never seen it any other way, and probably that's part of the definition. Is it's just you can't have multiple dimensions within one. So I'm gonna say yes. I know in like JSON or in different data structures, you could have missing pieces, so that kind of throws things off. But to be considered a tensor, or you have to have consistent structure. Okay, so matrix multiplication. So a key thing to this matrix multiplication, and we're going to be doing some of this tonight, is that see the blue numbers. Okay, this is a 1 by 3 vector or matrix. You can call it a matrix. We're taking that and we're doing a dot product. It's multiplication, sometimes just called a dot product, with a 3 by 3 matrix. So these numbers on the inside, the 1 and the 3, have to match. Otherwise, you cannot do the multiplication. Because the way you do the multiplication is you take the whole row of the first part, and you multiply it by the whole row, the whole column of the second one. So, and then you put that as your first value in your result. Now this is interesting because they do a 1 by 3 times a 3 by 3, they end up with a 1 by 3, which that's not a 1 by 3, that's a 3 by 1. So they technically did this wrong. I'm not using this one again. They totally did this wrong. I mean, basically, when you take this one and you multiply by this one, that gives you the 1 times the 2 times the 3, and the 3 times the 4. Okay, and you put that as your first, you line that up as your first column, not your first row. Yeah, because it ends up being 20, and then 10, and then 13. Your second column, you take this one, you multiply by this one. So 1 times 1, 2 times 3, and then 3 times 1. You add that all up, you end up with 10. And then you take this and multiply by your last column, 1 times 3, 2 times 2, 3 times 2, and you end up with a 13. So it's actually a 1 by 3, but they didn't show a 1 by 3 here. So sorry about that. I picked a bad example here. All right. So that's all the math I'm going to go through. One more piece of math that I didn't talk about that we will talk about here shortly. But yeah, so that's the base stuff that you need. Actually, there's a couple other things, but we'll go through it as we get there. As we develop, as we develop our network, this is what we're going to do. Okay, the first thing we're going to do is review some of the pictures we did in the past of neural networks, just so everybody's on the same page. Then I'm going to show you the XOR data set. We're going to create it. We're just going to instantiate it here. It's very simple. Then we're going to go through the feed forward process, how you go from the beginning of your network to the end of your network. And so we're going to do the math calculations, and then we're going to show the Python code to go along with that. So we can have the computer do this math, because it's not fun to do a lot of math by hand, even if I have a calculator. Computers are still better. So then we're going to show backpropagation, which means once we have our feed forward and we have the wrong answer, neural networks or any machine learning for that matter never gives you the absolute right answer. It just gives you an answer close enough eventually. But at the beginning, it's going to give you bad answers. We're going to take the error of that bad answer and pass it back through the network and update the network. So the first thing we're going to do is pass it back through one part of our network, the second layer, and then we're going to pass it back to the input layer and do a bunch of math, bunch of multiplication. Don't let it scare you. A little bit of calculus, tiny bit. So don't get scared. It's not complicated. It's a lot of stuff, very complex, but it's not complicated. It can be a little bit messy, and if I had a big whiteboard, I could make it much more straightforward, but we don't. So I'm gonna be flipping back and forth a lot. So yeah, and I'm gonna do that then. Oops. Then I will do weight updates once I have these. Once I've passed that error back through, I'm going to update the weights, which is with the definition of in a network, and then eventually end up with the right close enough answer. We can stop. All right, and after I go through all this, and then I'm going to pull in this Iris data set and apply the same exact code that we did for this XOR data set. We're going to do the same code, same stuff, same calculations, same math, no different. We're going to apply it to a completely different data set, completely different idea, knowledge base, and have it learn that. So we're building this generic learning algorithm here. All right, so review. A little bit of review about neural networks. Here's a picture of a perceptron, one neuron. You pass in a bunch of inputs, here M inputs to your neuron. You have one bias input as a given. And when I say pass in, I'm passing into this neuron, this two-phased neuron over here. This is the body, it's got two pieces to it. First part of the body is a weighted sum, and it's weighted by the weights, W1 through W0, 0 multiplies by your bias, and W1 through Wm multiplies by each one of the weights. So you multiply them, add them all together, take the answer, pass it through your activation function. And that takes potentially this huge sum, huge number, and brings it within a acceptable range. And here they're showing -1 to 1. Ours will be the sigmoid, which will be 0 to 1. And then you have your output of your neuron, the final answer. And that will feed into your next neuron. Okay, so that was perceptron. We have that same exact thing over here on the left. One neuron, a bunch of inputs. We're going to expand that to a two-layered network. That's a one-layered network. One neuron, one layered network. So one neuron because we only have one output, one answer we're trying to come up with, rather than our neuron giving us two answers, which neural networks can do that. We can get more than one answer at a time. We just have more than one neuron. So if we add a string of neurons in the middle, this is called the hidden layer, and it feeds to an output layer. You have all these other weights between your inputs and those three neurons in the middle. And these all are identical. All of these neurons do exactly the same thing. Bias and inputs, weighted sum, and then activation. This one, that one, and that one all behave the same way. Same calculations, same code. Okay, so, and all I've been talking about is the feed forward part of this. All right, so now let's talk about the XOR problem. And this is sometimes called the hello world example of neural networks, because it's very, very simple. It's a very small database. It's very unique in that it can't be represented by just one layer. It has to have a hidden layer, which we will get to that layer later. But here's the data for the XOR. You have X1, X2. When you have a 1 and a 1, that gives you a 0. When you have a 0 and a 0, that gives you a 0. When your inputs are different, it gives you 1s on your output. So this website here, when we're done with this, I want everybody to go and look this up. This is where I got this from. It's some consultant firm that specializes in machine learning. They do a blog. They have this nice development of this network, all the math, the best development I've seen. I really need to reach out to them and say, you guys did a great job with this. And I've looked at a lot of developments for this, explaining backpropagation, and none of them are as good as this. Probably there's some videos that might explain it, but I don't have time to go through every video out there that's explaining neural networks. doing my own. Okay, I'm gonna take a pause here and see what the questions. Why is the bias value 1? Okay, let me look at the other one. It's not more common to extract multiple answers results through multiple neurons. Could you please provide an example? Okay, so the first question, why is the bias value 1? It's 1 because that, let's go back, because that's the generic, go back. If it's 1, you multiply by some number and passes in, it could be anything because you've multiplied it, you've scaled it by this weight. So the fact that it's a 1 just makes it so you're always passing something in. You could have all zeros for your other weights, but your 1 coming in makes it so you can possibly have some kind of activation going on in this network. It's not just dormant. It's not quiet. That's the basic reason. It's at some point we may go into more development of that, but that's the main reason. And you don't necessarily have to have it, but it does help with the training. It helps solve some problems. Okay, and the other question. Okay, it's good because we're getting ready to answer that. That's easy to answer now that we've taken a look at this XOR problem. Okay, this gate, this XOR gate, it's one relationship that X2, X1, X2 can have. There's also like an AND gate, there's an OR gate, there's also NOR and all of those. Well, we could have those as other outputs on this network. And then have this neural network, same neural network, develop all of those outputs, all of those relationships. We're only showing one relationship, one output here, the XOR. So that's an example of learning more than one. You having more than, somewhere where you'd want more than one output. Okay. Please post your queries to all panelists and attendees so that everyone can view. Those queries, those questions were in the Q&A part. They were not on chat. And I guess I'm the only one that can see that. But I will read the questions, don't worry, Anvesh, but good call out. Okay, Manik is asking, why are we specifically using OR, XOR? The reason for that, I didn't go into that tonight, but I'll go into that more at some point, is that it requires a nonlinear relationship in order to model the XOR. You can't, all of the other ones like AND and OR can be developed with a linear relationship. Okay, we got a comment here from Shreyas. All the questions are actually visible in Q&A. Good. Okay, so got to look in the Q&A to see that. So anyway, yeah, I didn't start with the linear regression or linear model, which one neuron is a linear model. One neuron of neural networks is a linear model. When you add that hidden layer, it allows you to do nonlinear relationships. And we will go into this next time, why this is a nonlinear relationship versus linear. A lot of times that is explained at the beginning of these kinds of things, but this takes a lot to go through. So I skipped that as far as part of the explanation, but we will do that. Some nice pictures to go along with that. Okay, so the network that we're going to use to do this this model, this neural network model, is shown over here on the right. I've got two inputs plus a bias. X0 is the bias, and then X1 and X2 are shown here. So X1 is always 1. I then have 5 neurons in a hidden layer. named H1 through H5. And I've got weights, between each one of these layers. Each one of these neurons are inputs to this neuron, and then from this neuron, the output neuron. So that's our structure that we're going to go through. Very, very, very exciting. I picked 5. I didn't pick 5. That was in this code, in this example developed with 5. Probably could be done with 4, 6. That'll be part of your homework. Is try no hidden layer, see how well that works. Try bigger hidden layers, smaller hidden layers, more than one hidden layer. So that's for you to do later. Okay, so let's jump in here. Here's where I start to jump back and forth. So initially, don't worry about this feeding back, these arrows going backwards. When we get to the back propagation, we'll do that. However, I do need you to look at these names in here, like ZH1, AH1, Z0, A0. So H1 is in the hidden layer. We have these 5 neurons. I'm showing now these 5 neurons in the output. So Z and A are part of this neural network, this neuron. ZH2 and AH2 are in this one all the way down. Z0 and A0 are part of this one. Now the Z is the weighted sum of the inputs. A is the activation of that weighted sum. Same with this. Z is the weighted sum. A0 is the activation of that weighted sum. That's what I'm showing here. And the activation we're going to use is the sigmoid. And we'll get into that in a second. Okay, so that's the feed forward part of this. Now, once we get to the final output, we end up with this f of x. That's our f of x equals A0, whatever our final output is. We subtract that from y. Now, y is one of these. So when we feed in a 1 and a 1, we should get a 0. So that's x1, x2. So we'll get a y, a 1. So whatever we got when we stuck on the input, 1 and 1, and the output, we will feed that all the way through, and then subtract that from the actual what we should have gotten, which was a 0. Take that, square it, take half of it. That is our error term. Okay, so why is it squared? Because I want everything to be positive. So if I'm going to add up all my errors, I don't want a positive error offsetting my negative error. I want them adding. If I'm just as off negative than I am positive, I want that to show. So that's why I'm squaring it. Why am I dividing it by 2? You'll see. That's part of the simplification that is inherent in this development. Okay, and these other things we will get into, these partial derivatives, which I should have gone into that in the math part of it, but I didn't. Don't worry about it. We will go into it. Okay, so but what we're showing here, I'm going to go into this part later, the back propagation. So we got this error, and yeah, there's a contribution to that error of all of these values in here. Everything in this network contributed to this output being incorrect. That's a contribution. So, and what is that contribution? What we do is we take the partial derivative with respect to the error. So that is the definition of partial derivative, is the contribution. Okay, so let's get into the code at this point before we go deeper into the back propagation. All right, so here I'm going to jump out of this and into the code. So give me a second. I'm going to start up. Here's where it might be good to get some water. Oops. Dropbox. This is lecture 4. Okay, so now get Jupyter Notebook up and running. Take a second. Yeah, any questions, shoot them right now while this is running. Okay, if A equals sigmoid of Z, and why does A have a specific contribution? Isn't the contribution of Z sufficient? They will both have different contributions. Like if you change A a little bit, okay, that'll change the error a certain amount. If you change Z a little bit, that will also change the error a little bit, but a different amount. So that's what I mean by contribution. So both of them contribute, not separately. So you're correct in that part, but you can say they both contribute, but not, you don't add their contribution together. They just contribute in a little bit different ways. Hope that explain that. All right, so are we up here? We're up and running. I'm gonna go into here. All right, and what I'm gonna do is copy all of this to a second here. I'm creating a document that has this in it because I'm going to cut and paste. Okay, there we go. Out of here to my notebook. I copied it twice. Okay, so our first code. My mouse here going. Okay, and I'm going to create a new one here. Okay. So the first thing we're going to do is just pull in our libraries. The only library we're actually using here is NumPy. We're not using Matplotlib because I'm not doing any plots just yet. But I will when we do the Iris dataset. This one, the plots aren't that complicated. I mean, that would not be that complicated. Well, actually, they would be. It's part of your homework. You're going to add some plots. So let me put it that way. Okay. So first thing we're going to do is define our arrays. So I'm going to copy that here and run it. Oh, great. When I copy and paste, sometimes I get a little extra. Okay, so this is our XOR training set. It's a NumPy array. I'm added in the bias column. So it's 1, 1, 1, 0, 0, 1, 0, 0 plus the bias column. And then our output is 0, 1, 1, 0. can't be much simpler than that. So if I just print X, it's like that. If I print Y, it's like that. Okay, beautiful. All right, the next piece. Okay, we're not going to define our functions just yet. I'm going to pull in some parameters. That's the next piece that I have here. Copy and paste. So we'll talk about these parameters. Okay, so we'll get into this in more detail later, but we're defining a learning rate. And that learning rate is how fast we're going to learn. And we're going to talk about that much more at a later time, just not tonight, because it's a lot to go through as it is. But epochs, that is the number of times that we're going to go through our training set, all 4 rows of our training set. We're going to go through them 300 times. That seems to be a good number for this learning rate. You'll see why as we get there. And here I've defined a variable for the number of neurons in our hidden layer. So here that is. Okay, so the next thing that I'm going to do is I'm going to set up some weights. So that's here. And I'm setting up randomizing them. And how many weights? I'm basically, this function, this NumPy random function, it creates a matrix of, and I've got 5 columns, 3 rows. These are, for each of the 5 neurons in the hidden layer, and then 3 inputs. These are the weights in between the input layer and the hidden layer. So that's why I call it W01. If we look at our structure of our neural network, right here, we have 15 weights in between here and here. So it's 3 times 5. That's how many weights. So that's how we're defining it in our code. So now let's look at W12, which is the weights in between the hidden layer and the output layer. Here we've got 5 weights. There's 5 layers, 5 neurons in the hidden layer, 1 output, so just 5. If we look at our neural network, there's just 5 weights here. So here we're creating random weights, initializing it so that to something that it's like having your Rubik's Cube and the first thing you do is mess it all up. That's what we're doing here. Ooh, that's a good analogy. Remember that one. Okay, so that's all the code that we're starting with here, the setup. That's what I call the setup. Okay, so now I've got this defining functions here. I don't want to talk about that yet. Okay, it's, we're like, okay, so here's the code for training, but I'm not gonna, this is the end result, and I showed it at the beginning. We're now going to develop all of this, that and the functions, and develop it from scratch. So here's all of the math associated over on here on the left is all the math associated with feeding forward through our network. Let me bring this back up. So if you take a look, this first one here, something you got to keep in mind is that we have 4 values for x, for x1 and x2. So that's why we have I0 to 3. Okay, we're going to take each one of those of the x's and multiply by the weights and get our z's. And we're going to show what this looks like, you know, when we put the code in. But you know, here's the math for doing that weighted sum coming into Z, into that neuron, this neuron right here, H1, taking each one of these. Where's it here? We're gonna do a lot of this going back and forth. And I apologize. This is where if I had a big whiteboard, it'd be a lot easier to just point, but I don't have that. So we're basically doing weighted sum of all of our x's times the appropriate weights to give us the weighted sum coming in. We're going to take that number of each one of the weights of each one of the hidden neurons, pass it through sigma, which is our activation function, and get our activation output. This is the output of our neuron. Okay, so that's how we're getting the outputs of all of our hidden layers. Then we're going to they call this AH, but then they changed the name of it for some reason to HI. We're going to take each one of those outputs of those hidden neurons, multiply by its appropriate weight, and then we'll have Z for the weighted sum for the output neuron. Then we'll pass that through activation function, and then we'll have an A, you know, that the actual output of that. Now, okay, so that's the math for passing it through. What is our activation function actually? This is a sigmoid function. Whatever we pass in, we take 1 over the 1 plus the e to the minus whatever that is. And that gives us a nice function between 0 and 1, you know, gradually going up. At 0, it's a 0.5. Like if you pass in 0 for x, e to the minus 0, e to the 0 is 1. So 1 over 1 plus 1 is 1/2. So it's perfect. It makes sense. Hold on, drag this down here. Okay, then we have an output. We have an error on the output, which we went through this before. If the final output is different than our y, we subtract that, we square it, divide by 1/2. We'll talk about that. And that gives us our measure of our error. So that's what, so over here, this line of code, A0 and AH equals feed forward of x. So we pass in our x input, and we end up at the very end, AO. That's the very output of our network. Now, we also threw in this output of our hidden layer, and that we'll get to later as far as why we did that. Here is the code for that feed forward. What I did was I encapsulated it into a function. This right here is a dot product, a multiplication in matrix multiplication, and we use a NumPy function dot product. We take x, you know, that matrix, multiply it by our W01, our weights. That's this right here. So that's just the multiplication, and that gives us our Z for our hidden. Easy enough. And we pass that through our sigmoid. And we defined our sigmoid down here. I'll get that in a second. So we pass through that, and then we get our A sub H. And then we do exactly the same thing again to our second layer. That's our first layer, our second layer, you know, going out from our hidden layer to the output. We take the outputs that we just got out of our hidden layer. We do a dot product of those with our next set of weights. That's only 5. And then we get a weighted sum inside that neuron. We pass that through our activation function of sigmoid, and we get our final output. And okay, here's a mistake. I actually do return A0 and AH, which I added it later. So there should be two things returned, A0 and AH. So that's what we're doing here in the feed forward part of our learning. So forget about this for epoch and range epochs. I'm not going to go through that yet. I'm just giving you the code for doing our feed forward processing. So okay, then our error, which I'll get to that in a second. But first, let's just do this part in code. So let me jump over. Okay, I'm going to take this, separate it out. This, separate it out. And then go back to the lecture and fire that bad boy back up. Now, okay, so I'm going to define now in code, define our functions. Take these two functions, bring them over here, run that code. Okay, got a little too much here. And run it. Okay, so now I defined them. Big deal, right? And then I'm gonna run it. And then I want to pick this apart a little bit. So to run this, I'm gonna run this little bit of code right here. Okay, so now I've got AO and AH calculated. So now let's take a look at A0, the final output of our network. It's an array of 4 numbers. So we only have one neuron on our output. I got 4 numbers here. Why? Can anybody answer why? Put it in the chat. Meanwhile, I'm going to take a look at AH. Okay, I don't see anybody piping up in the chat. What it is I passed in X. X is not just one set of inputs. It's 4 sets of inputs. I ran this network, this neural network feed forward 4 times by passing that in. If I only passed 1 in, I only get 1 answer out. But I passed 4 in, so I got 4 answers. This is the answer that you would get if you pass in 1 1, 1 1, and a 1 for bias. And then here's the 1 0, the 0 1, and the 0 0. So that's why I got 4 answers out. This. Now the AH. When I passed, this is the output of the hidden layer. So I got 5 outputs, 1 for each hidden layer, hidden neuron. And then I got 4 sets of those because I passed in 4 different inputs. Okay, so is it XOR output by NW? I'm not sure what you mean by NW. Network? And yes, I think is the answer. Yes, okay. Yes, that's the XOR. That's the output. The Y is XOR. Is X1 XOR X2. So are those the right answers? Obviously not. What we were trying to get was 0 1 1 0. So we're off. Ugh, might as well throw a network away. And, who came up with this anyway? Actually, they were pretty smart because the next thing that we will do actually, at this point, the next thing we will start doing is figuring out how to adjust the weights, the W's, so that this is closer next time. So again, here's the output of the hidden weights, hidden neurons. Okay, so that was that part of the code. Let's go back. No. Okay. Oh, and the error, let's calculate what the error is based on this. Okay, so grab that code. That code is right here. Control C. Drop it here. And now print, I'll just do AO error. And of course, we'll get 4 answers. The first one and the last one are the furthest off. The ones in the middle are pretty close. Surprised? You know, those were the ones. Those are pretty close. These are way off. So this is the error, an error matrix C. Let's look at the sum of this. That is our sum squared error, sum of the squared errors divided by 2, which we're getting ready to see why that is. Don't worry, all is not lost. All right, so that's the sum squared. That's the next thing we're going to do is calculate this error. And now we're done with feed forward part. Now we're going to go on to back propagation. I mean, all of this math was fun. The next part is even more. So, okay, now we're going to go to the contribution. We're going to go heavy into the contribution part of this. And we're back to this picture here, where what we're going to try to do is, okay, what is the contribution to this error that if this W11 is off by this much, how bad will the error change? How much will the error change? If this W13 is off by this much, how much will the error change? That's the contribution of our weights. We're going to try to calculate that. And then what we're going to do is we're going to try to change these weights a little bit in the other way. You know, so if the W11 getting bigger makes the error get bigger, we're going to make W111 get smaller so that the error gets smaller. So that's our goal. Okay, the way we're going to do this is by doing a partial derivative. A partial derivative of the error with respect to that weight, one of the weights. Here I just picked one of them, W12, which is actually, I'm sorry, no. This W12 actually represents all of them. It's the weights from the first layer here to the second layer, the hidden layer to the output layer. That's the capital W12. Here's just like the weights within that matrix. So, but what does partial derivative mean? For those of you who've been far enough away from math, but I do remember this, partial derivative means if you hold everything else the same, okay, what is the contribution of this one value, this one variable? So I'm gonna hold all the other weights the same and see how much my error changes based on one of these weights, okay? So now there's this thing with partial derivatives that is this chain rule, which if we take a look, if we want to know what this is, we can rewrite this partial derivative as a breakdown of these values. Now, why did we pick these? Don't know just yet, but if you take a look, these, you can cross off these ones in the middle, like the partial A with a partial A, that's a 1, partial Z with a partial Z, that's a 1. So you can cross those out, and what you're left with when you cross those out is partial E with respect to W, which is what we're trying to find. So we just rewrote this. This is called the chain rule of partial derivatives. So given that this is equal to this, if we can find each one of these pieces, then we can multiply them together and we got our answer. We got our partial. We got our contribution. So time here. All right, so so what are all of these values? So basically what we're doing is going from this error, looking at each piece back to the W. The error came from the A0 came from the Z0, Z0 came from the AH1 through the W1 to the Z0, okay? Because we're holding everything else the same. So that's what we're looking at. We're saying, okay, what's the partial with E with respect to A0? That's just this, E to A0, that's one step. And then what's the partial of A0 to Z0? That's one step back. And then partial of Z0 with respect to W11. So let's calculate each one of these separately. Let's start with this partial E with respect to A0. Okay, that's just a derivative function. So we're going to take this y minus f of x, and they switched it around because it doesn't matter which way you write it. You're squaring it. To take this derivative, you subtract 1 from the exponent. So, and then you take that exponent and multiply by the outside. Basic derivatives. And what you get is f of x minus y. Wow, our difference in our output is what this is. Exciting. So another derivative that we want to look at is the partial of A0 to Z0. This will be the derivative of that activation function, 1 over 1 plus e to the minus x. Well, it turns out what that is this, a times 1 minus a. And we could derive that, I think I might be showing this later on, but this is just what it comes out to be. It's very, very simple. So this is the partial with respect to x of that function. Now let's go back and look at the function just so you see. This function right here. You take the derivative of this function with respect to x. And you can prove this, but we won't. So we just take it for granted that it's equal to this. So now we have this one. The first one we needed was this one. We now have this one. Let's get this last one. Partial of z with respect to w. Now, what is z? Z is this weighted sum. We take the a of the previous one times w11, take this multiplied by w12, blah, 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 add it all up. That's what z is. So we're going to take the partial of this with respect to w11. So we're going to hold everything else the same. Those, when you hold them the same, they contribute 0. And when you take the partial of this, take the derivative of z with respect to w11, this variable, this is 1 minus 1. You take w11 to the 1, it equals w11 to the 1. You subtract it, it becomes 1. Take that 1, you multiply on the outside, you end up with AH1 as your partial of z with respect to W1. So what they're saying is the contribution, that the amount of change this is going to change when this changes, it's just this value. That's what they're saying. That's the math. So what we're doing is we're taking the partial of each one of these, and we're showing that it's just equal to the output of the neuron before it. So now we have figured out all of these different contributions to the final error with respect to W12. And so if you take, what you do is you take this one, you multiply by this one, multiply by this one. And that's what we did here in the code. We said delta, the first error is just this minus this. It's the output minus y. And then, okay, something we didn't look at yet was this function sigmoid. If we take it, this sigmoid function not only calculates the activation, but it also calculates the derivative of the activation. So let's look at that function. We created the function back here. If I pass in derivative equal to false into this function, I get this x times 1 minus x, because I say if derivative, return that. If derivative is true, I'm sorry, that's if derivative is true, you get this. If derivative is false, and by default, derivative is false. That's how you do the Python. You are passing in this other value, 1 over 1 plus the exponent of minus x. And you have to use the numpy function for that. So I say derivative equals true because I want the derivative of the sigmoid and passing in a0 to get that, the delta of a0 with respect to z0. That's this one. Then I want this delta w2, and we show that that is just ah. It's this value here. So, and then we just multiply them together. And this is a fancy way of multiplying together matrices. What they did was, I'll get to the question in a second. What they did was figure out what way I can orient these matrices so that I can multiply them together. Here they just did a multiplication, a times, because this is just one value, this error. And here they had to take a transpose of the W in order to line it up just right so they could multiply it, so they can do a dot product. Okay, so then that gives you the delta output layer. That gives you this value. That's what they're trying to calculate. A question? Okay, so essentially by using a partial derivative, we find out the direction in which we have to proceed to minimize the slope or derivative of that particular weight. Yes, that's not the way exactly I'm explaining it. I'm kind of doing it more just with the math part of it, but in other lectures, we will show that we're actually looking at the slope of a derivative. Yes, Shreyas, that's basically what we're doing. Okay, so I know this is a lot of math, and it seems extremely complex. But we're just following the bouncing balls. We're finding the contribution of this weight to the error, and it's this part that you multiply by these together. So it's pretty straightforward. Okay, so now let's run this code and see what we get. Let's jump over here. Here's our code. So I'm going to run this little bit here that we just went through. Okay, I got errors, unexpected indent, because Python is finicky about our indenting. One of the reasons why it's so nice. So let's see what our delta output layer looks like. Okay, we got 5 of them because we have 5 weights. So each weight has a different contribution to the error on the output. Each neuron has a different contribution to the output, to the change of the output. Each weight coming out of the neuron, of the hidden neuron. Let's go back to here. That's these weights. There's 5 of them. Each one of them contributes a different amount. Okay, so that's that part. The next one is moving back. I now figured out how these need to change. I now need to figure out how these next weights, coming all the way back to the beginning. This is a part of our network. It's showing one neuron with our 3 inputs. There's actually 5 more here. I just showed one because we're just going to look at the 3 weights that are feeding one of the neurons. Likewise, we would do the same thing for all 5 neurons, all 4 other neurons. Okay, so what we're trying to find is the change. We're going to now figure out how to change these weights. We're going to see what the contribution of to the error of each one of those weights is. And we're going to, again, use a chain rule. If you see with this chain rule, if you knock out the AHs and the ZHs, the delta ZHs, we end up with what we're looking for. So now we're going to have to take this one step further with another chain rule. And this change in E with respect to H, break that down to another chain rule. And you can see that works out. That's this one up here. Now we need to go and calculate all of these values, all of these partials. So we've already calculated a couple of these. Like for instance, the change in E with respect to A0. We calculated that already previously. We calculated this one previously. We have not calculated this one. This is the change in this Z as a function of AH. Yeah, that's that one we did not calculate. We calculated the contribution of the weight of the change of the error with respect to the W, not with respect to this neuron. In other words, if this neuron changes at a certain amount, how much is the error changing? That's what we got to calculate. So we can easily calculate that by saying, okay, Z0 is it is what? It's the weighted sum of all the neurons. So the partial with respect to one of those neurons is just the weight of between that neuron and the output. So that gives us this final piece that we're going to multiply together to get this piece and feed it in there. Now we got to go calculate partial with AH with respect to ZH and partial ZH with respect to W. So let's look at that. Partial of AH with respect to ZH. That's just the derivative of our sigmoid. Simple. It's that same function, AH times 1 minus AH. And then we need to calculate this this contribution, or this partial ZH to the W, which if we do that, we can write that Z as this weighted sum, what they did here. Take the partial, and they dropped off the bias because I'm not sure why they did that. They really shouldn't have. They also should have said W0, W1, or W1, W2. But when you do take the partial, everything drops off except for this W basically leaves you with this X0, this X, which is a matrix of all three. This is actually 3 values. So I need to go back and rewrite this, but it is copied from that other that other presentation. So anyway, so we just have to plug all these values back in, multiply it all out, and we will have our partial of our error with respect to those weights. So let's look at how that looks in code. That's right here. So we're going to calculate our delta AH, which is this one, the delta of error with respect to AH. And that's multiplying those 3 things together, which is these 3 things. That's what they did. Then we're going to take the derivative of that sigmoid, derivative equals 2, and pass in the AH. So that is this part. And that's going to give us this value to multiply. And then we need to get our delta W1, which we saw was just X. W01, that's our first set of weights. Then we have to multiply those 3 together. There's a fancy way of multiplying them. You gotta do a transpose in order for them to line up, the columns to line up with the rows. And then we have this delta hidden layer. which is what we wanted to find. So, okay, so I got another question. The chain rule was devised based on available inputs that we can calculate with the inputs available. Would there be alternative variables we could use for the chain rule? Well, the reason why the chain rule works is because we're just moving backwards through we're chaining backwards through our network. Starting with the output, saying, okay, we're going to go this far, then we're going to go this far across here, we're going to go this far. We can't jump. You know, our neural network doesn't know anything, our output neuron doesn't know anything about these input neurons. We don't want it to. We want this to be a natural, every neuron looks exactly the same. It's just a function of its inputs. So we can only go so far, and that's why the chain rule works. Because we're just moving back one step to get to the input. We're back propagating the error back through the network using these, you know, it's really a very natural thing to do all these partial derivatives. It's like if this changes a little bit, then that changes a little bit, that changes a little bit. So that's kind of why we're having to do it that way. Hope that answers your question. Okay. So now let's run our code and get this other delta, and then we're almost done, which is good that we're almost done because we're almost to the end of the hour and a half. We're going to go a little bit over. All right, so let's grab our next set of code and go and run it. Again, oops. Take out our extraneous stuff. Okay, so now we have delta hidden layer. So I'm gonna grab it, copy, paste, run that. Got an array. I got 5 by 3 because we're going to apply this to 5 by 3 weights. So this is perfect. Here we're applying it to 5 weights. Here we're applying it to 5 by 3. Each one of those is the error, the contribution of that particular weight to how much the error changed. In other words, the partial derivative of the error with respect to that weight. Okay, so you can see each one of these errors did not change much. I mean, the error did not change very much with respect to each one of these weights. Changed much more with respect to these weights. Kind of interesting. All right, so now what we're going to do is update our weights. That's the next step in our process. So what we said was this partial, okay, that's how much the error would change if we change the weight this much. So why don't we change the weight a little bit the other way to reduce the error, and we're going to change it with 3 times as much. So you can pick this number. This is an arbitrary number. It's going to change how quickly we converge to the right answer, how quickly our weight's going to converge, and it may not converge. It may go too fast, and we will go into that and what happens if your learning rate's too small or too large. But that's our next function. Next code is just implement this right here. We're gonna change this weight just a little bit. How much are we going to change it? We're going to change it the opposite way of how much it affected the error. So what we're going to do is the next step is just that. Let's grab the code, run it. Again. Okay, now let's look at our weight set, the W01. It's an array, kind of looks like this. If we compare this to our array of weights back up here, they're changed a little bit. This was a point, which one did I do first? Okay, yeah, this is the same one. This is 0.58, it's now 0.57. So it got smaller a little bit. So that's what all of them did. They all changed just a little bit. W02, let's look at that one. I mean, W12. Those changed a little bit as well. They were, go back up and look at W12, it's 0.5, 0.3, and now, ooh, that changed a lot, 0.17, 0.07. So because these affected the error a lot, they changed a lot. The way to think of that. Okay, so we did this one time. Let's see if we're any closer to the right answer. And if I feed forward again, so let's go do this feed forward, and I'm just gonna run this code. Actually, you know what? I already have this code. Let's go back up. Okay, I defined it, and now let's run it. Are we any closer? This is this. We don't see what it was. They were higher numbers. So this is 0.7. This is 0.6. So it's really not that much closer, if anything. Actually, oh, these are our answers. Now let's look at what the error is. Let's see if our error is smaller. First of all, real quick, our sum error is 0.77. So let's see if our error got smaller. So I'm going to calculate the error, show what it is, and now, we are closer now. We're now 0.55. We were 0.77. That's exciting. All right, now I'm getting jizzed. All right, got 6 more minutes. It's good. I'm getting excited. Okay, so now let's run our code and watch what happens when we run this over and over and over and over and over again, and see that our error actually does get better. All right, here's our base code. I'm just going to step through this because it's a different kernel. Get all the way through, define everything. Okay, now, did I run it? No, I did not run it yet. So, all right, so this is a different, different random value, random set around random value, so our error is different. But if we look, our error is getting smaller as we go. Starts off getting a lot smaller, kind of stalls around 0.45 or whatever. And all of a sudden, we drop. Gets very, very quickly drops down to 0.01, 0.001. So it's kind of moving around. It's kind of getting into local minimums and then getting much better. So that's kind of what happens, and much more on that later. Okay, so after this trains, let's look at what our output now shows. This is what our output looks like after training 300 times, going through all the data 300 times, the 4 values. We now have 0, almost 1, and then almost 0. So see, we're close. So that's it. That's training neural network. The next thing, let's go back because I didn't get to the iris data set. And I may wait until next time for that one. You know what, this is very, very quick, but we'll look at this. We're probably gonna go over a few minutes. So now what we're gonna do instead of training on XOR data sets, we're going to train on the IRIS data set, much bigger data set. Now, the amount of code that we're going to have to change is almost nothing. This is it over here as far as what we're going to change. We're going to import one more library, sklearn, and what we're going to import out of that is the data sets, the IRIS data set. We're not importing anything else. So there's really not much that we're importing. And we're going to take that data set and we're going to create the X and the Y from it. So it's, you know, once you set the variable data set to be those data set, to be that data set, and then you break that into a, you know, your inputs, your X, and then your outputs. And what I did is I took the target from the IRIS data set. It doesn't come in the right, exactly the right format. I need it to be a vector in a certain orientation. I need it to be vertical, so it matches up with the X. So this is, so I transposed it. Okay, so let's go to the code, and promise we're almost done. So let's have the code here. So let's run it. I will separate it out. And we will step through it. So there's the first part. I load my data, I load the libraries. Come on, come on, come on. Then I load the data set, which we'll finish in a second. Okay, so now we have the data set and I can look at it if I want. So X is this. You guys should all be familiar with this by now. It's 4 inputs. Our Y looks like this. It's either 0, 1, or 2. Exciting. Okay, so now we're going to, everything else is exactly the same. Defining functions. Our parameters, we're going to be different. We're going to, since we have a lot more data this time, we're going to do our layering rate much smaller. And we'll talk about that, why that is. But basically, each piece of data, each row of data adds to the error. So our error is going to be much bigger. So we need to subtract. We need to make that much smaller. We need to divide that, you know, much smaller contribution. And we'll go through it 1,000 times. I'm going to use 10 neurons, 10 hidden neurons. Okay, and we're going to initialize the weights. Nothing different. Now here I added a couple of variables in here, the errors. So let's just run this. It's going to run. Done already? Yes, it's already done. 1,000 times, went through the data very, very quickly. So now we're going to look at the errors as we're, you know, now that we're done. So what I did was I total up the error, and total error is 25. So there's 50 data points for each flower type. So what ended up happening, and what I did was I broke it out between the 3 different data points, the error on each one. For the type 0, which was one type of flower, I have a very low error after training. For type 1, I have a low error. For the type 2 error, for the type 2 flower, I have a big error. I'm off most of the time. So we got to figure out why that is, and that's going to be part of your homework. So what I did here during my training is I put together these vectors that are the error over time, over all 1,000 times of training. So this is what the error looks like. Now this is different than what we saw before because this time it randomized differently and happened to train much quicker. Now if you notice here at the beginning, this blue one's my full error. The red one is error for the type 2. ended up at 25. The full error, total error, ended up at 25. The errors for the other ones dropped down to 0 pretty quickly. So this all makes pretty good sense so far. And now what I'm doing here is I'm lining up each data set, each data point, the 4 inputs, what the expected output should be, and then what my model calculated. So let's run this. Now, if you notice, all the zeros are about 0. They guess pretty good. All the ones are about 1. That guess pretty good. And then here's the 2. All of those didn't guess very well. You add all these up, you end up being, you subtract, square, add them all up, you end up with 50 divided by 2, you get 25. So that's the error. So that's it for the IRIS data set. Everything was the same except for the data set, and we came up with similar results. So present, let's see, I got a question here. In the XOR example, was the drop in error actually sudden, and why? It was, and we'll get into that next time. I'll explain why. It just, the error surface, if we graphed it three-dimensional, the error surface, all of a sudden you dropped off. You slid down the slide. You were pushing along, you're at the top, you know, you finally got to the steep part of the slide and you dropped down. Gravity pulled you down. So that's a picture of kind of why that happened. And we'll see all of that. It's fascinating. It's really great to visualize it. Okay, so here's some of the stuff we talked about before. And the question is, what's wrong? Why am I so far off on that one type 2 flower? And you'll notice that's part of the homework down at the bottom is why was that one off? Okay, so other homework assignments. Like I graphed the learning curve for the IRIS data set, I want you to graph the learning curve on the XOR data set. I mean, obviously the first thing on the homework is to reproduce what I did. You have my GitHub. You can pull it down. Another thing is to pull this XOR example up in TensorFlow Playground, which if you Google that, you'll see where it is, and it's cooler than anything. So just take a quick look at that. The XOR is actually one of the examples they have, so take a look at it and see how that looks. Then I want you to try messing around with, quote, hyperparameters, which, like the learning rate, try changing the learning rate, seeing how well it learns or doesn't. The number of hidden layers. Try the XOR problem with no hidden layers. Then try it with 2 hidden layers. That's going to be, you're going to have to figure out the math to do that, but I want to see somebody do that. And then change the number of hidden neurons, which that will be, that and the learning rate will be extremely easy. Those are just variables. But see what happens. See how the curve goes. See how these learn, whether they learn or not. Then try other activation functions. I did the sigmoid. You'll have to code another activation function if you're going to do that one. If you really want to get adventurous, look up momentum, drop out. There's a bunch of other hyperparameters of neurons. Code those. I'd love to see somebody do that. If you use a Keras model or scikit-learn model for neural network, those are very easy. It's just a matter of changing a function, a parameter of a function. But we're not doing that. We will do that next time. We will look at Keras, and those are great ways of using neural networks. It's just not the learning way. Other things that I'd love for somebody to do is do a fit, use a fit, create a fit function that does the learning, further modularize. I did the feed forward as a function. And then if you want to take this even further, create a class that, just like you're calling these other modularized functions within scikit-learn or Keras. And then add other hyperparameters to that class. So those are some great homework assignments. Have fun with it. Please, if you don't know where to start, please reach out to me. I will I more than welcome any questions along those lines, and I would love to help. It's very exciting for me, as you can tell the way I get into this. And if you have any questions, take a look at that article, but please reach out. This stuff is great. Until the slides are updated, could you please add some notes, highlights for the equations or notations which are incorrect or changed midway in the process? It'd be extremely helpful while reviewing the lecture. Yes, I will do that. Yeah, there were a couple of places that I feel are incomplete, mainly because of where I pulled them from. I always blame it on the other guy. So yes, I will do that. All right, gotta share the link here again. Oh, I'll go ahead and post that here, that link. Because it will take me probably sometime tomorrow. I'll have this, everything up there. Oops, all right, let's just click on it. And copy, paste. There you go. Any other questions? As I have before, I will be around for a few minutes to answer questions. Yeah, hope you guys are as excited as I am about this. I know this was hard in 1.5 hours and in the format we're looking at. And homework. Yeah, let's talk about homework for a second. The last set of homework I said was due tonight. I got, I think, probably 10 people that submitted some stuff. Please continue to submit it. I will go over the homework next week, next Thursday. I'll go over what was submitted and then some other stuff. And I kind of do that, give people 2 weeks to do the homework. I think that kind of makes sense. I know you guys are strapped for time, and I really appreciate those that got the stuff in earlier. That will definitely count more toward better accommodation in this class. But yeah, let's see. It would be excellent to be able to view the updated recording from the previous lecture cover. Yes, I know. I will do that this weekend before I do anything else. I will get the applications, get that taken care of. Thanks for the reminder, even though I know that's just on the back of my mind, like, oh, I got to do that. This process is not perfect by any means. So yes, I will want to say have the homework by next Wednesdays, but if not, I will not present it in class until the weekend, the week after that. Kind of do this staggered. So let me know if you have any other questions. I'll go ahead and stop the video and